So this is our next video in the section on 3.1, second order differential equations. And before we get to um, some of the techniques we'll be using to solve this, I just wanted to mention something about the graph. So in the, or I guess before, we talked about drawing a direction field, and we're not able to really get a direction field for a second order differential equation. Well, there's something else that happens that I forgot to mention last time, and that is if you're looking at solutions to a second order differential equation, it is possible that the solutions intersect many times. And so for second order DEs, can intersect many times. Remember the last time we were talking about two solutions cannot intersect like this, right? Because that would violate our existence and uniqueness theorem. But now, because the slopes don't depend just on t and y, they also depend on y prime, it is possible for two solutions to intersect. Okay, so that's just kind of a side remark for why we're not looking at graphs. All right, excuse me. So let's talk about a definition. We're going to get more specific about the type of differential equation we're going to be looking at. A second order DE is said to be linear. We're going to talk more about being linear in a few minutes, but if we can write it as in the form of y double prime plus, now we're going to use t, so p of t times y prime plus q of t times y equals g of t, or f of t. Okay, and so this is very similar to the first order, right? So the existence and uniqueness theorem is almost identical for a linear second order differential equation as it is for the first. If there is an open interval I containing, that's a maximum interval, containing t naught on which p, q, and g are all continuous on I, then there exists a unique, see that notation, solution to the IVP with y of t0 equals y0. And it's going to persist on the entire interval I, valid on I. So that part is very similar. That part is almost identical to what we did before. All right. So I want to make a few more restrictions before we start looking at solutions. Definition. If y double prime plus p of t times y prime plus g of t, well, that's q of t, q of t times y equals 0, the equation, the linear equation, is said to be homogeneous. Homogeneous. Why is that an Because we've already used that word once before. Okay, so hopefully it's clear from the context which version of homogeneous you're talking about when you're using that term. I will try to be very clear about the context. We're not going to be talking about first order equations for a while. So for us it's a little bit easier, so we will only refer to homogeneous equations having a 0 on the right hand side. By the way, this is called the forcing function g of t. Maybe I'll make a note here. This is our forcing function in our modeling. Forcing function. So in this case, our forcing function is 0. Good. Okay. And so homogeneous second order linear differential equations are the ones we're going to be working with. Is there any more restriction? Yes, there is. Oops. So we will consider second order linear homogeneous DEs with constant coefficients. That is differential equations of the form ay double prime plus by prime plus cy equals 0, where a, b, and c are real numbers. Good. So how are we going to solve these differential equations? Well, there's a technique in differential equations, tried and true, that's basically guess and check. We don't usually say guess and check. Normally we'll say we have an ansatz. So an ansatz is kind of a proposed solution. Ansatz. Our proposed solution is to, we'll try to let y of t be equal to e to the rt, and then we'll try to find values of r that satisfy our dE. Okay, and so this is what I mean by guess and check. We're guessing that our solutions are of this form. So what happens when I try to insert this solution into this differential equation? Well, y is equal to e to the rt. Y prime is re to the rt, right? Y double prime is r squared e to the rt. So plugging those into the differential equation, we have a times r squared e to the rt plus b times r e to the rt plus c, I'm up here, e to the rt equals 0. And so you'll notice that e to the rt factors out of the expression. Good. And now, by the way, we did this in section 1, or 1.3, I think, 1.3, our first day of class. Okay, so now, do we get solutions to this? E to the rt, the exponential function, is never 0, right? Because the exponential function is always going to be like that or like that. So e to the rt is never equal to 0. And so that's not going to contribute to our solution. And so therefore, our solution is r satisfies a quadratic equation, right? ar squared plus br plus c equals 0. Okay, and this has a special nomenclature here. This is called the characteristic equation. The characteristic equation. Okay, so we need to solve the characteristic equation in order to solve the differential equation. So how do we solve that? This is solved by using the quadratic formula, right? Quadratic formula. And we all remember that. R is equal to minus b plus or minus the square root b squared minus 4ac divided by 2a. Good. And so that's not the whole story. I do have to be a little bit careful because of the radical sign here, right? So the solution is going to depend on what b squared minus 4ac is. Okay, so let's list our choices here. If b squared minus 4ac is greater than 0, right, then we get, we have two distinct real R values, right? Let's say R is equal to R1 and R2. Good. Then what's the solution to our differential equation? Well, we're going to show in just a little bit that we're going to be able to, if we have two solutions to our homogeneous equation, we're going to be able to sum them to get the general solution. But I just wanted to summarize that first, and so we're going to prove this later. So to be proven later, y of t, our general solution, is given by c1 e to the r1t plus c2 e to the r2t. Okay, now what happens in the other two cases? If b squared minus 4ac is negative, we have complex values of r, and so we're going to have to look at complex numbers later. Okay, so that'll be in a future section. We'll look at that. And finally, the other section we'll look at later is what happens if b squared minus 4ac is 0. So that only gives us a single value of r. And so that's also going to be taken care of later. Okay, so in this section, we're only going to be looking at cases where we have two real values of r, and in that case, that's our solution. Good. So I'm out of time. I'm going to be, we'll come back with another video with some examples.